Okay, good morning, everyone. So, in last lecture, we start talk about the preparation. Means we have discussed enough regarding the property of nanomaterial. The size of the material, if a small enough comparable to the critical length scale of the semiconductor, the property will change. Venn diagram will change because of a quantum confinement effect. We give an example of optical property and also some electrical application as well. So this is the fundamental why nanomaterial is so interesting, because the property is different. Okay, so you can explore new applications. Since we know they are useful, then now we have to know how to make them. So talking about the growth, we start to mention we have mainly focused on two types of growth. One is a liquid phase synthesis. The other is a gas phase synthesis. In terms of a liquid phase synthesis, it's a precipitation process. Means that you have achieved a so-called supersaturation state. The actual concentration is so high, and it makes the system become unstable because the actual concentration is even higher than the theoretical limit. The system cannot maintain such a state for a long time. So the free energy is so high. So you want to change its own state to reduce the free energy by precipitation. Okay, that way you start the nucleation and also followed by a growth. Okay, so in the liquid phase synthesis, last time we mentioned, in order to prevent it grow into bulk material, you can have such a way to to protect it or inhibit it from nano into bulk. Okay, so you can use a molecular ligand capping. Actually, this way we mainly talk about the surfactant capping of the nanomaterial. In Jason's part, we'll talk about two stabilization methods. One of them is steric stabilization. Basically, it caps the nanoparticle surface with a molecular or ligand. Okay. Of course, you have to consider what are the functional groups that may interact effectively, specifically with this particular material. I mean, it's not universal. If you talk about oxide, some functional group interact with it effectively. If you talk about the gold, metallic, maybe another group of functional group that interact effectively with it. Okay, in the stabilization part, they will give some examples. And also you can inhibit the growth by limit the reactant, amount of reactant. You also can consider use a physical template, like hot template, like AAO template, okay? But we also need to separate the growth and the nucleation from each other in order to get a uniform nanoparticle size. We actually focus more on microemulsion and gel as an example to discuss the detail of the growth. Hydrothermal, soft thermal actually is quite important. First of all, it is important. Just because of time limit, we are not able to cover this. But this method basically is quite straightforward. It's a thermal decomposition of chemical to produce the material you want and precipitate out in the solution. Okay. We start to talk about what is a nucleation. Nucleation have a so-called homogeneous nucleation and heterogeneous nucleation. The way to distinguish them is basically if there's a foreign species acting as the nucleating aid. Okay, we use this as an example. Okay, do you have a finger? If the nucleation starts on the surface of the finger, that is the heterogeneous nucleation. And homogeneous nucleation have a narrow size distribution. Heterogeneous nucleation have a wide size distribution, means it's not uniform. Homogeneous nucleation require high concentration, mainly most cases require so-called supersaturation state. Heterogeneous nucleation, not necessary. Sometimes even it's not supersaturation, still the nucleation can start it. Actually, in the gel part, I will come back to this plot. I will come back to this, sorry, not this plot, this concept. Come back to this concept again to discuss about how we can make core shell nanoparticle. How we can make core shell nanoparticle based on the concept of heterogeneous nucleation. Okay, later. So actually, we talk about how to separate the nucleation from a growth by, inject a suitable precursor into a solvent at a high temperature. But in this way, although the nucleation starts very quick and the material precipitates out quick, you get a uniform nanoparticle because you separate the nucleation from the growth. But in many cases, you don't achieve a very good crystallinity because you are not able to allow the atom to arrange themselves into a crystal kind of ordered arrangement. Later on in the growth part today, we'll show you why, why you need a long time to arrange this atom. Then you can get a good crystallinity. So that will link. And we mentioned about supersaturation. So how to achieve supersaturation? What is a supersaturation? Supersaturation meant this state. Actual concentration higher than the equilibrium concentration. Means it's about the limit. But this is a transition state. Okay, so it won't be stable. This value will decrease through the precipitation. And this value finally will equal to the equilibrium. By then, the nucleation can stop. Okay, so in this state, the definition of the degree of supersaturation can be given by this equation. Actual concentration divided by the equilibrium. If this value is very high, that's a high supersaturation. If this value is close to 1, that's a low supersaturation. Okay. So now we can move to start to talk about growth. Growth is a very complicated, it's a complicated process. Many factors will affect the growth process. There's a kinetic factor which will affect the growth, affect the morphology of the nanoparticle or shape of the nanoparticle, even size of the nanoparticle. Then, in turn, it will affect the property of the nanoparticle. Okay, these are the kinetic factors. There will be reaction rate, how quick the chemical react with each other, the transportation rate of the reactant. Once you put the reactant into the solution, how quickly or how fast they diffuse within the liquid, meet each other, and then start the reaction. Accommodation process. Once the reaction started, it will generate a new atom, new molecular. How those new atom or molecular will be absorbed on the nuclei. Nucleation started, generate nuclei. And those newly generated atom or molecular should be absorbed on the surface of the nuclei for this nuclei to grow bigger, become nanoparticles. Okay, so this accommodation process, actually later on, I will talk about it will affect the crystallinity. It will affect the crystallinity. And last one is a removal and a redistribution of the material. Actually, during this kind of growth process, the atom can be absorbed by this nuclei, and actually some atom also can go away from this surface of the nuclei, goes back to the solution. They come and they go. It depends on which process is dominant, whether it grows into bigger particle, or actually it might even disappear. There's a critical radius of the nuclei. If the size of the nuclei smaller than the critical radius, you won't be able to grow into a particle. If the size of the nuclei is bigger than the critical radius, actually you will be able to grow into a nanoparticle. It's called critical radius. I thought some of you probably have touched this concept in previous third-year course. No? Okay, it's fine. It's not so important, because last semester some student came to me, asked me this concept of critical radius. Then I explained to him. I say, how you learn? He say he learned from previous course. Then that's why I mentioned a little bit. I thought you already touched it, but it's not fine. Don't worry. It's not so important at this moment. So basically, just have an idea. The atom may adhere. Atom may also, detach, but based on which process dominant, the particle will grow, or sometimes even the nucleus can even disappear. Okay, so this is referred to this part. Those kinetic factors actually can be adjusted by simply changing the synthesis parameter. For instance, I want to increase the reaction rate. What happens? I can simply, let's say, increase the temperature. I increase the temperature. In most cases, it will increase the reaction rate. So this is an example. You can change those synthesis parameters in order to affect those kinetic factors. Then it will lead to change of the property, lead change of the morphology, lead to change of this size of the material. Okay. So those synthesis parameters, including let's say concentration of the reactant, how much reactant you put into the solution, temperature, at what temperature you start the reaction, okay, and pH value. pH value actually is very important for sol-gel reaction. Sol-gel reaction, for this reaction actually involve two processes, hydrolysis and condensation. It will typically generate oxide. You can use it to generate oxide nanoparticles. So depends on the pH value, the process, means the reaction process, can be completely different. For acidic condition, means the pH value is very low, the process may take a few days, even weeks. If it's a basic condition, let's say it's a pH value high, 14, 13, okay? In that case, the same reaction, same type of material generated within a few minutes, simply based on the pH value, okay? Later on in the sol-gel reaction, will show you the two different routes. Through acidic condition, there's one reaction route, and through basic condition, there's another reaction route. Okay, that give a difference in the reaction rate. And also how the reactant will be mixed together and what sequence you add them, one and another, they will also affect the reaction as well. Okay, even sometimes affect the morphology as well. So those are the parameters. Those are just an example of the parameter. Of course, there are others you can consider. Okay, maybe even gas environment will cause some additional change. Okay, so here by changing those parameters, you affect the kinetic factor, and that will change the property of the nanomaterial. For instance, crystallinity or the particle structure. These can be affected by the reaction rate, or sometimes even the impurity. If you existence of some chemical you do not want, it will actually affect the crystallinity as well. So how the crystallinity can be influenced by reaction rate? Actually, this is related to the accommodation process. Typically, fast reaction rate, that will, the newly generated molecular and newly generated atom will be more in a short time. So this attachment process will be quick. So this actually will related to the how the nanoparticle grow and how the atom arrange them from each other. What is the crystallinity, first of all? What is the crystallinity? Crystallinity, actually, this is a TM picture of a nanoparticle. When you look at the individual, those dots, bright or dark, those are atoms. Those are atoms. So this is the arrangement of the atom in such a way, highly ordered next to each other with a defined position. This is a periodical arrangement of the atom. That's the crystallinity. If you have such a way that it's a fully ordered arrangement, that's a good crystallinity. If it's a disrupted, not ordered arrangement, that's a amorphous. It's a poor crystallinity. So in that case, imagine right now you have a nuclear already generated during the nucleation process. And now we have one atom start generated by the reaction, and then this atom can be absorbed by this nucleus. And let's say once it's absorbed, not necessary this atom already in the right position within to form this kind of order arrangement. Maybe the right position for this atom should be in this red dot. Let's say in the red dot. So this atom should start some so-called surface diffusion in order to achieve the right position. If the accommodation process and this reaction rate is relatively slow, so the atom should have enough time for it to diffuse along the surface to reach the right position. But if the accommodation process is very fast and the reaction rate is very fast, so before this atom can diffuse into the right position, other atoms already start to deposit or absorbed by the nuclei. Maybe some atom already block the diffusion part of this atom to prevent it from a very ordered arrangement to give you a highly crystal structure. So that's why if you have a very fast accommodation process, you might not achieve a good crystallinity. Okay, you might have a low accommodation process to have enough time for the diffusion to take place. Same idea, actually, in the previous part. If you have very fast reaction, fast nucleation, as well followed by a fast growth process because you inject it at a very high temperature, you might not give enough time for the atom to diffuse into the right position. You don't have a good crystallinity, right? The same idea right here. You should give some, time for the atom to diffuse in order to form a good crystallinity. Of course, that requires certain energy as well. You have to have enough energy to promote this atom to start the diffusion as well. Okay. Particle morphology can be influenced by the surface tension and the supersaturation and nucleation and growth rate. First of all, for the nucleation and the growth rate, this actually refers to this process, the separation process. If you have fast nucleation, you actually stop the nucleation in the growth step already. You actually separate them from each other. You will have a relatively uniform nanoparticle in the site. If you don't have a fast nucleation, have a very slow nucleation, you will have such kind of mixture. You will have a non-uniform nanoparticle. That's referred to the last point right here. In terms of a supersaturation, the effect of supersaturation on the morphology will be shown you in the next slide. So we will see it later. What about surface tension? How the particle morphology can be affected by the surface tension? We know the nanoparticle have a very high surface area, and the high surface area in turn will give you a very high surface energy. So any system don't want to have a high surface energy. Want to have a high energy, so-called free energy. You want to reduce the total energy. So how to reduce the energy? So what is the surface energy? First of all, what is the definition of surface energy? Surface energy is surface tension multiplied by the surface area. Surface tension multiplied by the surface area of the particle. So right now, let's say I have some particle with a given volume. You already made this nanoparticle with given volume. If the surface tension value is very high, that means the surface tension multiply the surface area. The surface energy will be high. So right now, if the volume of the nanoparticle is somehow already fixed, so the nanoparticle, we don't think about agglomeration rate, agglomeration yet. We just think about the particle itself. The particle already generated. The particle has certain volume, and right now the surface tension is very high. So how the particle can reduce the total surface energy? The only way is to reduce the surface area. For the same volume, the particle say, I want to reduce my surface area to minimum in order to reduce the surface energy. Because surface tension is given, surface tension is very high value. Only way to reduce the surface energy is to reduce the surface area. So for a given volume to given volume nanoparticle with a given volume. So what is shape? It have a minimum surface area. It's a spherical. Spherical shape give you minimum surface area with a given volume. This is geometry actually. This geometry. So that's why in nanoparticle synthesis, if you look at the many experiments, you will see most cases the particle is spherical. It's because they want to reduce the total surface area. Spherical shape have a minimum surface area. In some cases, if the surface tension, this value is not high, it's relatively low. In that case, the surface energy in this case may not be so high because the surface tension itself already high. The system may not necessary to reduce its surface energy by minimize the surface area. So in that case, sometimes you might see other shaped nanoparticle, cubette. Okay, this is a cubette. They can be related to the crystal structure of the nanoparticle. Some cases you make an iron oxide, Ms4014, and if you made into a relatively slightly bigger, let's say 100 nanometer in that size, you can actually see a lot of cubic shaped nanoparticle can be generated rather than this spherical. That's because the surface energy in this case is not so high, not play a critical role. But if the surface tension is high, in many cases you will see the particle is spherical. Okay. So just now we mentioned about the supersaturation is also important. You know, supersaturation, the degree of supersaturation is defined by actual concentration divided by the equilibrium concentration. Okay, and so if it's a low supersaturation, means the value is close to 1 maybe. So you actually can get this kind of a nanoparticle well-formed, small, well-separated from each other, not uniform in terms of size, not agglomerate from each other. If the degree of supersaturation is increased to relatively high value, and now many times you will see a lot of dendritic kind of growth because the concentration right now is high. Means the concentration is high since the supersaturation is relatively high. So you are not able to separate the nucleation from growth very effectively because the concentration is high. The nucleation can keep on taking place, right? So some nanoparticles already formed, already in the growth process, but some nucleation still can start it and generate nuclei. The nuclei can absorb on the previously grown nanoparticles, start another growth. In many cases, you will form this kind of branch kind of a dendritic growth, okay, because the concentration is higher. And if it's very high supersaturation, then the density of the nuclei is so high, so it will cause agglomeration. Like this case, you see there's a well-formed nanoparticle, but they're highly agglomerated. The nanoparticle, the density of the nuclei is so high within a limited volume of liquid, so it will form this kind of agglomerated particle. Okay, so this gives us an idea about the effect of degree of supersaturation that will affect the morphology. Okay, and talking about growth itself, there are some mechanisms we have to think. Actually, first of all, what is the growth process? Growth process involves a few sub-steps. First one, you have to start a reaction. The reaction generates the atom or the molecular. Second one, the generated atom or molecular has to diffuse within the liquid to come to the surface of this nuclei, to come to the surface region of the nuclei. Then it will be absorbed by the nuclei itself. Then the nuclei grow into a bigger particle. So these are the few steps. Actually, it will give you in the next slide. Next slide will show you this 4 step. So it depends on the particle, whether it's a big particle or if it's a small particle or it's a big particle. The growth process itself can be controlled by either a surface absorption process or controlled by the diffusion process just now mentioned. Okay, each of this controlling process actually can affect the morphology of nanoparticle in terms of uniformity, the size uniformity of the nanoparticle. Okay, so if it's a small particle, the growth is controlled by the surface absorption process. If it's a large particle, the growth will be affected by the diffusion process. Okay, so we will explain this a little bit more in the next slide to give you a more clear idea. So just now I mentioned 4 steps of the growth. Generation of the growth species, which is through the reaction. Diffusion of the growth species, within the liquid. Absorption of growth species onto the nuclei, and let the nuclei grow bigger. And then last one is the growth of the nuclei into a particle. So this 4 steps, for the growth process, you have to wait for the 4 steps to complete in order to finish one growth cycle. So it's actually in the definition, which of the steps is the slowest one. If let's say it's the slowest one, all other 3 steps have to wait for it to finish in order to finish one growth cycle. And that slowest step will become so-called determining step, or it's the controlling step. Okay, whichever that step is the slowest one, then the other step have to wait for it to finish. So that slowest step, we call it controlling one. Okay, so that's the case. We can group this growth process into 2 process. If the particle is big, if the nuclei is big, the diffusion process as compared to the absorption process, okay, maybe I should start with the small particle. Let's say if the nuclei is small, so the atom generated, the atom diffused to this region. However, if the nuclei is very small, surface areas are small. So in order for this atom to find this nuclei, to be absorbed by this nuclei, take some time. Because the surface is so small, the nuclei may not effectively absorbed by the particle. It might miss it. But if the particle is big, let's say the nuclei is big, so atom go to this region easily can be absorbed by the particle because the particle, surface area is big. in any closed region can easily be absorbed. So that's why we say if the particle is small, so the incorporation of growth species, which is this referred to the absorption process, is the slowest step. If the particle is small, so it takes some time for it to be absorbed. So this is the slowest step. If the particle is big, so this absorption process is relatively quick, then the diffusion might consider as a slower one. So the diffusion will become the so-called controlling step. So that's how we separate them. That's why for small particle, interface control, the absorption process is slow. For large particle, it's diffusion control because the absorption is quick. The diffusion is relatively considered to be slower. Okay. So in this two steps, it's quite interesting. We find out the outcome of the particle can be completely different. The uniformity of the nanoparticle can be completely different if they are controlled by different steps. Okay, let's first look at the diffusion control process. Diffusion control. Okay, so when the concentration of the growth species reduced below the minimum concentration for nucleation, so growth continue. In the case of diffusion limited process, means that diffusion is considered to be the slowest one. The growth process is controlled by diffusion of the growth species. The growth rate, okay, gives some equation. Although it's not a focus of mathematical calculation, but we have to understand what's the physics meaning of this one, especially regarding the answer part. Especially regarding the answer, means this equation can be mathematically solved. I give you some answer, and what's the physical meaning of the answer will tell you what is the outcome of this growth process. Okay, so this left-hand side is the dr by dt. That actually tell you if I have a nuclei, and this nuclei will start grow into relatively big particle along with the growth time. So t is the growth time. R refers to the size, the radius of this nuclei. So this actually tell you how the nuclei should grow bigger. What is the radius change along with the time? How the radius change along the time? How quick, how fast, and how big? Okay. This one actually related to so-called diffusion process. So it should related to the diffusion coefficient. Diffusion coefficient of the species in the liquid, concentration gradient, the concentration gradient between the 2 points in order for this diffusion to take place. And last one is related to the surface area. It's a volume, it's a molar volume of the nuclei, and R is the, as just now I mentioned, it's the radius of this nuclei. So it's relatively referred to the surface. Okay, so this defines how the diffusion will take place, and that will affect the growth process, how the nuclei, the radius of nuclei grow bigger. This equation can be solved, but I spend less time. I give you the answer part. Okay, this is how this refer to the answer. This is a KD is a coefficient. First of all, explain some coefficient. KD is a coefficient related to this term. KD is just it's a coefficient. It's just a symbol to relate to this part. Okay, and so this is actually it's an answer calculated based on the previous equation. And what are the meaning right here? R is a radius of the nuclei. Sorry, should be radius of the nanoparticle. It's in the final product, radius of the nanoparticle. If you say delta R, what is a delta R? Delta R actually refers to the difference. You might have, let's say you have two nanoparticles. One is this much big, one is the other size. So delta R refers to the difference between the two radius. This is a meaning, okay, delta R. Of course, R is the size, refer to the average size of the nanoparticles. R0, okay, R0 actually refers to the original state. The growth starts from a nucleation, end of the nucleation. So by the end of the nucleation, you have some nuclei already. So R0 refers to the average size of the nuclei. Average size of the nuclei. Let's say my growth starts from here. These are the two nuclei, although size highly different, but you just consider that at least there are two nuclei. So R0 refers to the average size of these two. Average size of these two, okay? Delta R0, that means similar difference of the nuclei. Size difference of the nuclei means the size difference between the two nuclei, okay? Size difference of the R0, okay? So Kd is the coefficient just now I mentioned. T is the growth time, along the growth time, okay? So this one actually is the answer of the previous calculation. It tries to tell you the size difference in the final product. If we just simply look at this equation, let's say we just simply look at the equation. So if this R0 and delta R0 is the initial state, that means already defined. As long as you have the nuclei, all this value already set, okay? And Kd is a coefficient already given by the system. So if the T increase, means that now you start your growth, the T will start to increase, right, along the growth time. Now what happened to your size of the nanoparticle? You will see that this whole term should decrease. If T increase, this whole value should decrease because T in the bottom. It's very straightforward, right? Although not linear, but it will decrease. So that tells you, initially you have some nanoparticle, sorry, you have some nuclei with some size difference. What value is given, although I don't care, okay? Then, after certain growth time of T, the final product, the size difference should keep on decrease. What does that tell you? That means the nanoparticle will become more and more uniform because size difference will keep on decrease. Size difference will keep on decrease. So that's why I draw a cartoon right here to give you an idea. Initially, I intentionally to draw two big different particles. I mean, the size is big difference. You have one nuclei, you have another nuclei, the size of big difference. And that is defined by the delta R0. But right now, along the growth time of T, after some time, the particle both grow bigger, but you see it will become more and more uniform. The nanoparticle size difference will become less and less. So this is good. We want to achieve a uniform nanoparticle. We want the size difference become less and less. Okay, so actually in the growth part, we want to achieve a diffusion control in order to get you the smaller size difference. We call it monodispersed. Monodispersed means the size is highly uniform. That's very small size difference. Okay. So this is regarding the diffusion control. What about the other two? The other one is the interface control, right? The absorption process. So that refers to smaller nanoparticle. Actually, so when the diffusion of the growth species is rapid, diffusion is quick. So then the absorption process is considered to be smaller process. So the growth rate is controlled by the surface process, means the absorption. So there are two mechanisms for surface process. Actually, even within the growth, surface absorption process, there are two kinds of growth. One is so-called mononuclear growth. The other is a polynuclear growth. For mononuclear growth, it's given by this kind of cartoon. Means when the atom attach on the surface of the nuclei, the atom has to form one complete layer, then the second layer can start it. In contrast, we have a so-called polynuclear growth. So the atom comes to the surface of the nuclei. Before this complete layer form, the second layer already started. Even the third layer can start it. This is called polynuclear growth. You are not necessarily form one complete layer in order for the nanoparticle to grow. Okay. So let's just first talk about mononuclear growth. Mononuclear growth, actually, this process is proportional to the surface area of the nanoparticle. So that's why the radius of the nanoparticle change along the time is proportional to the surface area, which just simply use r squared to represent the surface of the nanoparticle. There's some coefficient. This coefficient actually is related to some system value regarding the liquid, regarding the material as well. But that one, if the system defined, that value is defined. So again, we can solve this equation, solve this function. Okay, get the idea how the radius should change along the time. This can be solved. This one, if we solve it, again we get a function like this. We get an equation like this. The meaning right here is the same. Size difference. Size difference of the final product. Size difference of the final nanoparticle. Delta R0, again, is a size difference of an initial nuclei, which is a set value. If you have a nuclei defined, have the nucleation process stopped already, so this value is given. So right here, if you look at this equation, Km is some constant already given by the system. R0 is the initially average size of this nuclei, or also it's let's say the set value. Then only thing change again is the time. Growth should be when the growth continues, the growth time should increase continuously. So this value, of course, by the definition, should be always less than 1. It's actually it's true. Okay, it's set by the boundary condition. So the t, if it's increased, it will make this value become smaller. If it's always less than 1. So this value will become smaller if t increase, and finally this whole part will increase. Well, that will be in contrast to the previous diffusion control. That tells you if t increase, this value will keep on increase. That means the size difference will increase. You have a you have a nuclei. After some growth time of t, then the size difference becomes bigger. You have a non-uniform nanoparticle. The nanoparticle is not become non-uniform and the size difference will keep on increasing. And that's not what we want. We want a uniform nanoparticle because we want the property to be uniform. We want to know the nanoparticle used for certain application, and that property has to be defined. That property has to be uniform. The property is related to the site. Property of the nanoparticle directly relate to the site. Of course, you want a uniform nanoparticle, uniform size nanoparticle. But in this one, when t increase, you actually become non-uniform. You have property also become not uniform. That's not what we want. And this cartoon just give you your idea to represent the meaning of this equation. Basically, initially you have some nuclei. Okay, I use 2 nuclei to represent it. Average size is R0 is given. Size difference delta R0 is also given. After growth time of t, both grow bigger, but the size difference will increase. The nanoparticle become not uniform, and this problem will become severe and severe. Okay, the size will become different, will become bigger and bigger. Okay. So what about the polynuclear growth? This is another process. Okay, in the polynuclear growth, the growth rate of the particle actually is independent of the particle size of time. This is observation. Okay, and the growth rate is a constant. Constant is given by this equation. It's relatively simple. You know how the size of the nanoparticle should change along with the time. It's a constant. Kp is some constant related to the system, liquid, material of the nanoparticle, and temperature also. Okay, so but once those parameters defined, then the Kp is a constant. So what again? We need to solve this function. Okay, get the answer of this one. What we get is a delta R, which refers to the size difference of a nanoparticle, equal to the delta R0, which is, the size difference actually doesn't change. But if the size difference doesn't change, how we can get the understanding what should be the uniformity? Whether the particle become more uniform or the particle become less uniform. If the size difference keep on as a constant. I give you an example. I have 2 nuclei. Initially, one is a 10 nanometer, the other is 20 nanometer. Size difference, 10 nanometer. Now, after growth time of t, they grow bigger. One become 90 nanometer, the other become 100 nanometer. Size difference keep on at 10 nanometer. What you consider? Whether they are more uniform, they are less uniform, or the same. If I would say the latter one will be more uniform. 90 nanometer, 100 nanometer. Although the size difference is 10 nanometer, but somehow I have a feeling this become more uniform. Do you have the same feeling? No? No? Okay. So how we can define the uniformity? We have to, mathematically give a definition. What we do is the uniformity should be, if we define precisely, should be the size difference divided by the average size. This gives a more, to me, I think it makes more sense. We call it dispersity. If this value becomes smaller, that means it's like more uniform. If this value is big, that means less uniform. Okay, this is called dispersity. If the dispersity value is big, that means nanoparticle not uniform. If the dispersity value is small, that means nanoparticle quite uniform. This is how we define. So if we define in this kind of equation, you can see that this delta R divided by R, based on this equation, actually they can write it in another form. Again, it's related to time of t. If the t increase, that actually refers to the particle grow bigger. The average size of the particle grow bigger. So this whole dispersity value should decrease. Decrease, that means it will become uniform. Okay, so this is the idea. Initially, you have two nuclei with a given size, difference. After some time of t, both grow bigger, and the average size of the nanoparticle become bigger, and the size difference, however, maintain as a constant at the beginning of this two nuclei. But the uniformity of the nanoparticle also become better. Means the dispersity decrease. The value of this. The only reason that dispersity decrease is because this value will increase. Although this one keep as a constant, but this value will increase. That's why it makes the whole thing decrease. As just now I mentioned, 10 nanometer, 20 nanometer, as compared to 90 nanometer and 100 nanometer, the latter one should be more uniform, considered to be more uniform. Okay. So although I talk a lot about the mathematics part, but actually the only thing I want you to at least have an impression is this plot. Okay, this helps you. You get the idea about this one, the previous calculation, you may even not necessary to remember. Okay, you just have a feeling of this plot. Now I plot the dispersity of the nanoparticle for three cases. One is the diffusion control, one is the polynuclear growth, one is mononuclear growth. Okay, and the y-axis is always dispersity. That tells you how uniform the nanoparticle is. The x-axis actually have two kind of coordinates. One is along the average size of the nanoparticle. The other one is along the time. Okay, if you print it, it's very small, probably you even cannot tell. This is t, this is r. Okay, one is t refers to the growth time. On this one, this is growth time. This one is r, which refers to the average size of the nanoparticle. But both refer to the same chain. You know, when the growth time increase, the nanoparticle average size should also increase. Refer to the same chain. Okay. So right now, you plot the size dispersity as a function of just look at the average size of the particle. You will see that the dispersity, actually this one is the initial state, referred to the nuclei. It's not zero. It's some value right here. Zero origin should be here. This is origin. Of course, initial state cannot be zero, right? You always have a nuclei. You always have a size difference. So if it's controlled by diffusion control, if this growth is controlled by diffusion, you will see that the size dispersity will keep on decrease, and that will give you a uniform nanoparticle. If the growth is controlled by mononuclear growth, the size difference will the dispersity will keep on increase, and that means the particle is not uniform. Dispersity increase, value become bigger, the particle become not uniform. If the growth is controlled by surface control, by the polynuclear growth, the dispersity will also decrease, but to a less extent as compared to diffusion. The particle will become more uniform, but less extent as compared to diffusion. So right now, the similar change will be represented in this growth time coordinate as well. Similar change. Okay. So right now you can see that we want a diffusion control. Okay, as compared to all other two process. Now the question is how you can make the system become diffusion control. We know that diffusion control gives you a uniform nanoparticle. How you can make the growth become diffusion control? Think about it. You have to make the diffusion become slower. You have to make the diffusion become the slowest step. then the growth will become diffusion control, right? Based on the definition just now we mentioned. If the step is the slowest one, that will become the controlling step. That will make this one become diffusion control. How you can slow down the diffusion? How you can slow down the diffusion? That's another question. In reality, in your experiment, you might need to think about it. How I can slow down the diffusion within the liquid. You might choose a system have a low diffusion coefficient. How the diffusion coefficient related? Might relate to temperature, might relate to some other parameter. What about a liquid? If I choose a highly viscous liquid, the diffusion also can slow down. Highly viscous, prevent the effective diffusion. What about the concentration gradient? If I somehow play with it, decrease the driving force. Concentration gradient actually is a driving force for diffusion. I play with it, I again can slow down the diffusion. So those are the questions you can think about. How to, because in the reality, in the experiment, there are many, from experiment to experiment, there are many factors not exactly same. Okay, you have to consider for the real, for the concrete example, and think about parameter can slow down the diffusion process. Okay, so let's take a break. If you have any question to come to discuss with me. Okay, everyone. So let's continue our discussion. So just now, I just emphasized this plot. You can just have a feeling of it, or even you can enjoy it. I think it's quite straightforward, right? 3 lines, different shape, refer to this size dispersive. Will give you a clear idea about how this nanoparticle size should change along the growth time or along the average size of the nanoparticle. So now those basic parts we have finished discussed regarding the nucleation, regarding the growth, how the parameter will affect this 2 process. In fact, any nanoparticle growth should start with the nucleation, then followed by the growth. Then later you should consider about this agglomeration or this kind of causing problem by choose some stabilization process. So now we start to talk about a particular technique. The one we start with is microemulsion. Microemulsion is a very, to me, it's a very interesting technique. This one have a so-called precise control of the nanoparticle size, composition, shape. It gives you a lot of ability to control it precisely. However, they also have a drawback. The drawback is a low yield production. It never being able to make into a even gram level, I would say. Probably always in a milligram, tens of milligram. Use a large quantity of liquid, but final amount of product is relatively limited. So this is a widely used technique in a lab-based research, but not much company use it for their main production. Okay, but it still is a very useful technique to give you a clear idea how to manipulate each of the parameters in order to control the size of the nanoparticle, shape of the nanoparticle. Okay, so what is a microemulsion? Microemulsion actually is a mixture. Microemulsion makes 2 solvents which cannot mix from each other. We intentionally choose one is, let's say, water, the other one is oil. Oil and water, when you mix them, they cannot form a mixed solution. They will form 2 separate components. So in the system, typically we can have oil and water, and in between, we actually can put some surfactant. The surfactant we added is so-called amphiphilic surfactant. Surfactant sound molecular. If this is amphiphilic, that means the surfactant have one side is a hydrophobic, the other side hydrophilic. That's the reason we call it amphiphilic. Okay. So this surfactant, if it's amphiphilic, makes them mixable in both hydrophobic, let's say oil, hydrophobic liquid, as well as the hydrophilic, which is water. A typical microemulsion can be illustrated by this kind of cartoon. If I put small amount of oil, let's say octane, hexane, with large amount of water and some reasonable amount of surfactant, 3 components together, I will form something like this called microemulsion. That the oil, since it's a small amount, form droplet. There are many droplets, not just one droplet. Oil form many droplets. And outside this droplet, there's the water. Water serves as a reservoir, as a medium. So small oil droplet dispersed within the water, okay, within the water media, okay. Between the oil droplet and those water, there's a surfactant, amphiphilic surfactant. The hydrophobic component, typically hydrophobic component is an alkane chain. It's a chain, okay, CH3, CH2 alkane chain. This one will be located inside the oil. The hydrophilic head, this one in the water. So this is how typically an amphiphilic surfactant should be located between the water and oil. Of course, I can make another kind of microemulsion. I use less amount of water, but large amount of oil. So in that case, I form an emulsion like this. Water form droplet. One for the droplet. Of course, there are many droplets. And oil becomes the media. Okay. Then this droplet dispersed in the oil media, and in this case, the surfactant will also arrange them accordingly. This hydrophilic head should located in the water. Hydrophobic tail will located in the oil. Okay, this is how they arrange them together. So typically, this is a microemulsion. It's a mixture of oil, water, surfactant. So although they are optically isotropic, okay, optically you look at them, they are also isotropic. They are not properly described as solution. They are microemulsion because they are mixture. They are mixture of 3 components. They are not form solution. Okay. Microemulsion are microscopically homogeneous mixture of oil, water, and surfactant. The driving force to form a microemulsion is to reduce water-oil interfacial tension. The reason is that you have a surfactant in this interfacial region, and the hydrophilic characteristic, hydrophobic characteristic of this amphiphilic surfactant can make them be a very nice interface layer to reduce direct contact between the water and the oil, to reduce the interfacial energy, interfacial tension as well. So microemulsions are thermodynamically stable. They can be stable for a few hours, even a few days. But in the long run, it actually finally will be disrupted, will form a separation of water, oil, and in between some surfactant. Okay, why we need to make them into such a kind of arrangement? Why we make them into such kind of arrangement with a droplet dispersed in the media? Actually, the purpose is that we try to allow the chemical only soluble in the droplet. I choose some chemical, let's say only soluble in water, not soluble in oil. So then those chemicals will only confine within this droplet and allow the chemical reaction to start within this droplet. Then this droplet will use as a so-called nanoreactor. So the reaction only within the droplet. If I control the droplet size to be, let's say, 5 nanometer, 10 nanometer, or even 50 nanometer, then the particle size will be confined by the droplet size. Okay? In fact, I can precise for a given microemulsion, we can precisely control the droplet size by playing with some parameter. Mathematically can calculate it actually. You can define the droplet size. Then you can define the nanoparticle size. So that's why I say the microemulsion can precisely control the nanoparticle size by allow the reaction only happen within the droplet, called the nanoreactor. Okay, but one thing I have to mention, in experimental setup, 99% of the reaction of the synthesis is carried out in this water in oil microemulsion, or we call it reverse micelle. Reverse micelle is water in oil. Micelle is oil in water. So that's just the terminology. It's just the name how we define it. 99% of the reaction is carried out in this so-called water in oil microemulsion in the reverse micelle. The main reason is related to the selection of chemical. It is very easy to choose some chemical that only soluble in water but not soluble in oil. That is for, let's say, for some inorganic nanocrystal synthesis. Let's say I want to make copper oxide. I choose some copper precursor, copper chemical. I can choose some copper chemical only soluble in water but not soluble in oil. Copper chloride, copper sulfate, easy. But in this condition, it is very difficult to find some salt, some chemical that only soluble in oil but not soluble in water. No. In many cases, you find out they are both soluble. They are soluble in water as well as soluble in oil, if some organometallic salt. So that's why make this kind of synthesis less popular. It's the only reason is the selection of the salt, chemical. Okay, so 99% we use the reverse microemulsion. Just now I also mentioned, it's not just size control. We also can do so-called shape control. The way to control the shape actually is by control the shape of the droplet. Shape of the droplet. How the micelle, how the shape of the droplet form. If it's spherical droplet, you turn out to make this kind of, let's say, spherical nanoparticles. If I made into a so-called channel shaped water droplet for the micelle, I can make this kind of nanorod or anisotropic system. Okay, so this is one of the advantages. Of course, as just now I mentioned, all the chemical is dissolved within the droplet, within the water droplet. So the composition control has become easy. You just simply tune up the ratio of the chemical you dissolve and allow all the chemical to involve in the reaction. Then you have a chemical the composition control as well. So this is also another advantage. So how we can achieve this kind of shape control? I mean, since we say you can achieve a spherical, you might also achieve this called a channel. So how we can make them into different shape? This actually related to one thing called phase diagram of the surfactant. We use amphiphilic surfactant. We call it some molecular, maybe a long chain molecular, and that one is related to so-called phase diagram. When you put this surfactant into the water, depends on the into the liquid, depends on the concentration of the surfactant, depends on the temperature. They actually will aggregate into different shape. Okay, this is a typical phase diagram for one particular surfactant called CTAP. That's just one surfactant commonly used in the lab. So you can see that if the this is the amount of surfactant in the in the liquid. In this case, actually in water. So if the concentration of the surfactant is very low, you actually form a discrete individual molecular. So now you start to increase then along the axis, increase the concentration. Above this line, this is one boundary called critical micellar concentration 1, CMC1. It's a critical micellar concentration 1. That's the concentration value along this boundary. Above this concentration, you form aggregate. The molecular start to aggregate and form this kind of micelle, a spherical shaped micelle. Now, you further increase the concentration of the surfactant. About another boundary region, critical micellar concentration 2, you form the shape of this aggregate change to this kind of cylinder shape, okay, or we call it a channel shape. The aggregate of the molecular become this channel shape. Further increase the concentration, you can form this hexagonally packed cylinder shape, okay, micellar. And then, if you further increase the concentration, you can form a laminar. Laminar shape means that you see that's one layer of the surfactant, another layer of the surfactant, okay? You are in between, that's a layer of the liquid, layer of the droplet. Well, using this kind of shape control is quite useful to control the droplet shape. If I have a spherical droplet, make spherical nanoparticle. If I have a channel shaped droplet, I make anisotropic shaped nanoparticle, nanorod, even maybe nanowire. If I have this kind of laminar shape, layer shape, I can even make a nanosheet, nanoplate. Okay, all that's quite useful for the control of the shape of a nanoparticle. Okay, so but here I have to mention this particular phase diagram, although there's some value already given, right? It refers to a particular surfactant. If you change from one surfactant to the other, the phase diagram will change slightly, but the general change is similar. Only thing, maybe the boundary value will be different. Means the concentration boundary value will be different. The temperature range may be slightly different. But this kind of general change will be similar. Always change from a spherical to a cylinder, then to a closed pack cylinder, or even to the laminar shape. This one later on will be also useful to make some so-called mesoporous material as well. If some of you doing FIP in this, probably already been familiar with this phase diagram of the surfactant. Okay, so based on this kind of concept, we can make the different shaped droplet. That droplet can be used to make a variety of material. Semiconductor, maybe lead selenide, as we discussed in the tutorial. Okay, some sulfide as well. Metals, gold, platinum, silver. Metal oxide, okay, iron oxide, nickel oxide. All this can be used to. All this method can be. All this material can be used to be produced by this using this method. Okay. They have an advantage. Very small particle can be prepared. Okay, I can precisely control the droplet. Actually, in the tutorial, we have one practice on how to estimate what the parameter we should change in order to change the droplet from 60 nanometer to 30 nanometer, and then even you can control it to even smaller, okay? The particle size and shape can be very well controlled based on this phase diagram. The size actually is referred to the next concept, water to surfactant ratio. We will calculate that in the tutorial as well. And also good composition control, as we said, all the chemical will be added within the droplet, allow them to react completely. You will get this composition control. But disadvantage, you have a low production yield. You use a large quantity of the liquid. Let's say in the microemulsion, right? You actually, in the reservoir region, you already use a large quantity of oil, but that oil not involved in the reaction. Use a very much liquid, but only the droplet involved in the production. That's why you get a small amount of nanomaterial, normally in the milligram, even tens of milligram. And you have to use large quantities of liquid. Okay, so this is the drawback. It's not good for the scalable production of nanomaterial. So how another question right now, if I made a microemulsion, how I can induce the reaction only within the droplet? Means I dissolve the chemical into the droplet. How I can effectively make sure that the reaction only starts within a droplet, not, let's say, if I put them into the water, they will start mix immediately and the reaction should start immediately. How I make sure that the reaction only happens in the droplet? Okay, this is some procedure right now to control this reaction to make sure that the only start in the microemulsion. Typically, let's say A plus B, you get a reaction, give you some, let's say C. This is C is the product we want, okay? So in the preparation process, let's say typically is that we actually have to dissolve A, the precursor, into the water before forming the microemulsion. So this will be a problem. You see, if I add A and B together in the water, they are mixing. Maybe the reaction started. Before I form the microemulsion, you lose the control of the size. You lose the control of the shape. So how typically A and B together we can control them in order to the reaction only happen when the microemulsion form. We can make two microemulsion. One, I have a bigger, I have water, some water mixed with oil. Before I put the water into this oil, I first dissolve A into water. Then this water will mix with oil and add some surfactant. I maybe sonicate it for some time. The magnetic stir for some time. They will form this microemulsion. Okay, typical procedure is that you add small amount of water, large amount of oil, and surfactant. You just magnetic stir it for maybe half hour. You will get this droplet within this water reservoir. Okay, droplet of water in the oil reservoir. Okay. Now you can similarly you can make another microemulsion. I dissolve B into the water, small amount of water. Then I put this water into the oil. Then add the surfactant again. Magnetic stir it for some time. You get another big of microemulsion. In order for the reaction to take place, you just simply pour the microemulsion B into microemulsion A. Actually, during this mixture, typically all this micelle, the droplet, they always start under so-called Brownian motion. They are actually moving around because their temperature. The temperature is always moving around. So many times they will collide between each other. There's a collision, okay? And during this collision, if A and B droplet meet each other, they will form so-called dimer. This is dimer. During the formation of a dimer, the content between them will exchange. Content between them, it will exchange. Then A and B will mix, and then you form this, allow the chemical reaction started. If somehow happen, if A collide with A, that's fine. There's no reaction happen. After some time, although they exchange content, there's some no reaction happen. After some time, this dimer was dissociated into two droplets again. So that's okay. The microemulsion doesn't change if A meet A. Only when A meet B, there will collision. There will be there will be dimer, and the dimer will exchange the content, and A and B mix. If it A meet A, then fine. Although A, you change content, but there's no chemical reaction, still be the original microemulsion. So this is the way how the chemical reaction can happen in the microemulsion, and this chemical reaction only happens within the droplet. Okay, so normally we don't prepare one microemulsion, we prepare more than one microemulsion, allow them to mix from each other. So this is a typical procedure. The reverse micelle are subject to continued collision due to the Brownian motion. Formation of the dimer during the collision, although the lifetime is not very long, it's quite short. Okay, during the lifetime of the dimer, two reverse micelle will exchange the content of their core before decoalescing into two droplets and become an equilibrium. Okay, so this makes reverse micelle highly suitable as a nanoreactor. We call it a nanoreactor. Size and the shape can be fairly uniform. Okay, simply by changing the size and the shape of the droplet. How the shape can be controlled just now related to the phase diagram. How the size can be changed. Later on we'll discuss about the water to surfactant ratio, and that one will be practiced in the tutorial as well. So this is a general procedure, how we can make some nanoparticle. Let's say we want to make a platinum nanoparticle. Okay, platinum nanoparticle can be used by mixing platinum chloride, some platinum chloride precursor, with a reducing agent we call it hydrazine. It's N2H4. This is actually slightly toxic, but highly reducive. So once the hydrazine meets the platinum chloride, we will reduce platinum 4 plus to platinum 0. Then we'll give you a nanoparticle, platinum nanoparticle. So how we do it? Typically, we make one microemulsion containing the platinum chloride dissolve into this water droplet. Make another beaker of microemulsion, allow hydrazine to be dissolved into this water droplet. Then you pull them together. You will see the collision between the droplet form dimer. Then this hydrazine meet the platinum chloride and make a platinum 4 plus become a platinum 0. Then start the nucleation and followed by the growth. Finally, you have this nanoparticle. Right now, this nanoparticle actually is not protected by the surfactant, although it is located in the water droplet. So without removing the droplet, without removing those surfactants, the nanoparticle is stable. But if we do some centrifuging and do some washing process, you remove the nanoparticle from this droplet and this surfactant environment, the nanoparticle may easily agglomerate because their surface is clean, the surface no protection. This surfactant only stabilize this water droplet. This surfactant not necessarily interact with this platinum nanoparticle. This is the amphiphilic surfactant previously we introduced to stabilize the water droplet only. So somehow you can also consider add some other surfactant, some molecular, to cap the surface of the platinum nanoparticle in order to prevent them from agglomeration. If you look at the TM picture, you will see those are the nanoparticles. With protection, they can be separate from each other. If they are not protected, you might end up to see some picture like this very high supersaturation case. Okay, you might end up with let me go back. This one, you might end up with some picture like this. Platinum nanoparticle end up with a high agglomeration if surface without protection. Okay, so you have to consider the protection. You have to consider the protection. In the adjacent part, stabilization part, will give you some idea about how to protect the nanoparticle from each other. Okay. So talking about the size control, just now I mentioned, okay, we have to consider one ratio called mole ratio of the water to surfactant. We call it water to surfactant ratio. Should be W naught. W naught like this, okay. It's the amount of water divided by the amount of surfactant. Typically, if this value is very big, that means your droplet should be big. If this value is small, the droplet will be small. That can be used to control the droplet size and control the nanoparticle size. The other factor can also affect the formation of the droplet in the microemulsion. First one is the type of surfactant. Just now I mentioned the phase diagram closely related to the type of surfactant. different surfactants have different phase diagram. Obviously, surfactant should play a very important role on how the droplet should form, right? Second one, type of solvated ion in the droplet. Okay, how this can affect. Actually, this refers when you dissolve the chemical into the water droplet. This chemical may generate some ion. Let's say previously, platinum chloride. You dissolve it into water, you will form a platinum 4+ ion in the liquid. This is a solvated ion. And now, for the surfactant, which used to stabilize the water droplet, if it's ionic surfactant refers to that the surfactant itself is charged, some charged species. If it's an ionic surfactant, then this platinum 4+ should have a Coulombic interaction with the surfactant. And typically, the ionic surfactant, the hydrophilic head is charged. Okay, this hydrophilic head is charged. So in that case, you have a Coulombic interaction between the ion and this surfactant. That kind of interaction can affect the formation of the droplet, can affect the shape of the micelle, how the molecule should aggregate, since there's an electrostatic interaction. If it's a non-ionic surfactant, then this kind of ion may not have a big effect. So what is ionic and what is a non-ionic? In the next few slides, we'll have an example when we discuss about the HLP concept. Okay. So this one is a very important concept. Give you an example. How this water to surfactant ratio should affect the nanoparticle. This is the work done by myself, by me. I use a microemulsion to make iron platinum nanoparticle. I mix the iron precursor with the platinum precursor. Then I change the W0 value. I change the W0 value from 4.5. I get roughly 20 nanometer nanoparticles. Now, if I change add more amount of surfactant, less amount of water, I change the W0 to a 0.6, smaller value, I got a smaller nanoparticle of around 4 nanometers. You can see that simply by change the W0 value, you can change the same material from a big to smaller nanoparticle. Okay, so this gives you idea. In the tutorial, we'll give a practice estimation of this W0 value in order to precisely control the droplet size, not particle size, but droplet size. So this is a general procedure of synthesis of a nanoparticle using microemulsion. Typically, 2 reactants, if it's a 2, okay. If you have 3, you can consider make even 3 microemulsion. But not necessarily each chemical should have a 1 microemulsion. Sometimes, if let's say A plus B plus C give you some product, let's say D or something. If A and B not react each other, you can put them together in 1 microemulsion. Then C you put into another microemulsion. Still, you only need to make it into 2 microemulsion as well. Okay. Of course, if A react with B and B react with C, all 3 react with each other, you might consider have to make 3 as well. Okay, 3 microemulsion as well. So all depends on the real experimental condition. So this one you dissolve into 2 microemulsion, A in the 1 water pool of microemulsion, another B in another water pool of microemulsion. They'll mix A and B by put them together. You have the coalescence of the water droplet. Then the water droplet also decoalescence. Then finally you have this precipitation started. All this will follow our previous discussion of the nucleation and then growth. All the previous basic concept should apply right here. Okay. So for the microemulsion, after product, as just now I mentioned, we should consider the mechanism for stabilization. Typically, you can consider the molecular capping, or we call it the steric stabilization. Or you can consider use the electrostatic stabilization. Both techniques were discussed by later on by this in the stabilization part. Okay, steric stabilization refers to that you have your nanoparticle, you put some molecule into the liquid, and those molecules have functional group specifically interact with the nanoparticle surface, can attach on the nanoparticle surface to form capping layer. This will protect the nanoparticle from agglomeration. Another way called electrostatic stabilization. This is another concept. You have a nanoparticle dispersed in the liquid. Right now, I induce some ion in the solution, and those ions are charged. Those ions may preferably attached on the surface of this nanoparticle, make the nanoparticle surface become charged. And this makes the nanoparticle of the same charge, all positive charge. Let's say they attach, chlorine ion attached on the gold nanoparticle. Then, sorry, that's the negative charge. So all negative charge. Then when the nanoparticle getting close to each other, you'll form this kind of repelling force. That's the electrostatic repelling. And that will make the nanoparticle stabilize. So this is the electrostatic stabilization process. So this gives you a explanation, okay, how this nanoparticle can stable. In the steric stabilization, the surfactant can choose polymer or other organic species, okay. And in the electrostatic stabilization, you can choose the chemical absorption of the charged species in the surface. Most cases, iron. It's iron, okay. So we have the idea right now in a microemulsion, we can control the size, we can control the shape. But one thing we have to discuss, how we can make a stable microemulsion. Actually, it's not necessary. If you randomly choose a amount of water, amount of oil, and randomly choose some surfactant, if you mix three together, it's not guaranteed you will get microemulsion. You might always form a separation of three components. You have one layer of water, you have one layer of oil, you have in between some layer of surfactant. And not necessary to give you the droplet in the reservoir. So they have to have some mechanism to make sure that this microemulsion can be successfully prepared by choosing the right component. Okay, this mechanism is so-called a HLB concept. It's actually a very old concept. It's related to hydrophile lipophile balance. Hydrophile lipophile balance. It's referred to the hydrophobic balance in this system. You know, water is considered as a hydrophilic component. Oil considered as a hydrophobic component. Amphiphilic surfactant have some hydrophobic characteristic, some hydrophilic characteristic. These three have to form a balance. If this balance is satisfied, then this microemulsion can be stable. If this balance not satisfied, you cannot form a stable microemulsion. So all this is related to this HLB concept. Okay, hydrophile lipophile balance. There's a balance between the hydrophilic, hydrophobic. Okay. So what is the HLB concept? What is the balance? Actually, in a microemulsion, in order to form a stable microemulsion, each component, first of all, each component always have a HLB value. Each component. Water has some HLB value. Oil has some HLB value. Even the surfactant has some HLB value. Okay, those can be either mathematically calculated or you find out from some handbook. Okay, refer to the particular molecular. And the requirement is that the HLB value of the liquid actually refers to the mixture of the oil and the mixture of the oil and the water, two components at least. So these two components mixed together, although individually they have a different HLB value, as a mixture they will have another so-called effective HLB value of the mixture. This effective HLB value has to be equal to the HLB value of the surfactant. Then this microemulsion system can be stable. If there's a large difference between the HLB value of the liquid, which is a mixture, and the surfactant, then you will have a problem. You won't be able to make the stable microemulsion. You will form a separated layer of this liquid and the surfactant. Okay. The effective HLB value of the mixture, the water and the oil, actually can be calculated. Actually, sometimes we are not necessarily choose one surfactant, means one amphiphilic surfactant. Sometimes we can choose also can choose 2 surfactants or even 3. Again, you have a mixture, and this mixture, the HLB value can also be calculated. Okay, so first of all, let's consider about the HLB value of each component. For water or oil, the molecular is relatively simple. We always can find out the HLB value in the handbook, from some handbook. Okay, you also can calculate, but the value is already there. It's straightforward to find out. If sometimes we have a very complicated molecular, as a, let's say, surfactant, it's a polymer, the structure is not previously has been well studied, and the value cannot be found out in the handbook. We actually can calculate. We can calculate the HLB value. It's quite straightforward. So the surfactant, if it's a non-ionic surfactant, what is a non-ionic surfactant? By definition, is that when you put this surfactant into a liquid, they don't generate any charge. It's typically a molecule like this, only composed of some alkane chain and some ethoxy or methoxy group, OCH3, only composed of carbon, hydrogen, and oxygen. Quite simple molecular, but there can be many different repeating units. Okay, so this is very straightforward. You put this one into the liquid, into water, no charge will be generated on this molecular. We call it non-ionic surfactant. The way to calculate the HLB value in this surfactant is simply by calculating the weight percentage of the hydrophilic component. What is the hydrophilic component in this system? Actually, it's those ones who contain this oxygen. Okay, this ethoxy group, they have 2 repeating units. Ethoxy group is a hydrophilic component. The other part, this CH3, CH2, and this CH3 group is a hydrophobic. Okay. So in this case, to calculate the HLB value, simply calculate the weight percentage of the ethoxy group in this molecular. Of course, there's some coefficient. Multiply by 100%, divide by 5. This is based on the experimental observation. Okay, people tend to use this kind of calculation. Actually, HLB value is a relative from each other. So you add or not, it's okay. Okay, so in this case, for using this one as an example, to calculate the HLB value, we have to add this hydrophilic component, which is 88. Each one is 44. Ethoxy group. So 2 repeating unit is 88. Then divided by the molecular weight of the whole molecular, which is 132, and then multiply by 100, which is referred to here, 100%, and then divide by 5. Okay, then you get the HLB value, which is 13.3. This is the way we calculate the HLB value of a non-ionic surfactant. What about the ionic surfactant? So what is the ionic surfactant, first of all? Ionic surfactant is those ones, they contain iron. Once you put into the liquid, the iron can detach from the surfactant and leave some charge group in this molecular. Let's say this is a typical ionic surfactant, sodium lauryl acid. So this side, sodium sulfonate group, once you put into water, this sodium ion will detach from the whole molecular, leave this part 1 negative charge. And that's why we call it ionic surfactant. If you put into a liquid, it will then generate charge. The way to calculate the HLB value of the ionic surfactant actually is even simple as compared to previous one. This one is even simple. Only thing you need to find out is the HLB value of individual functional group, add them together, and another constant 7 right here. Another constant 7 right here. So how I can find out the value of individual functional group? Actually, there's a table. The table right here. Okay, let's come. You can find out the table in many handbooks, even online. Okay, let's look at this one as an example. In this sodium lauryl acid, that contain 1 CH3 group, 11 repeating unit of CH2 group, and 1 sodium sulfonate group. Okay, and of course, when you calculate, don't forget the 7 right here. So CH3 group in the handbook, I can find out, oh, CH3 group, negative 0.475. CH2 group, also given right here, same value. Sodium sulfonate group, given right here, positive. So you simply add all this value together, but don't forget there's 11 repeating of this CH2. You have to multiply that value by 11 and add another 7. Finally, the value around 37. Okay, this is the HLB value. So quite straightforward. Add HLB value of individual functional group together, and you will get this HLB value. So now, talking about the mixture. We know how to calculate the HLB value of if it's a liquid, if a simple molecular, we can find out from a handbook. If it's a complicated molecular structure, we can do the calculation based on either non-ionic surfactant or ionic surfactant. How about the mixture? Right now, you're talking about mixture of a liquid, let's say water and oil. You also can choose two surfactants together added into the microemulsion. Then you have to also consider effective HLB value. For the case of a mixture, you're always using this so-called lever law. Lever law means a weight fraction of that component multiplied by the HLB value of that component. Okay, so right here, if we say we are talking about the mixture of a two surfactant, we mix the sodium lauryl acid, which just now we calculate the HLB value, and another surfactant, which is sodium oleate. It's another ionic surfactant as well. So assume we can do the same thing to calculate the HLB value. And if the weight fraction, we know it, then you can use the lever law to calculate. The effective HLB value for this surfactant mixture is 0.4, referred to 40%, multiply 37, plus 0.6, multiply 18. Then your effective HLB value is somewhere in between the two values, 25.6. 25.6 is between the two values. This strategy actually is very important. This strategy is actually very important. In the tutorial, we'll discuss this one in detail. Similar concept will apply to water and to the liquid, means the water and oil mixture. If you know the weight fraction of your water, know the HLB value of the water, and then you have this HLB value of the oil and the weight fraction of your oil, you can calculate the effective HLB value of your liquid. Then this HLB value of the liquid has to be equal to the HLB value of the surfactant. Then your microemulsion will be stable. Otherwise, your microemulsion will not be stable. And why I mentioned this concept is very important, because in many cases, if I already choose the liquid, I already choose the amount of liquid, certain amount of water added into certain amount of hexane. Okay, I try to form a microemulsion. Then the job is I have to choose the right surfactant in order to match the HLB value of the liquid. However, in some cases, if happen by nature, that kind of value of HLB value do not exist, this kind of molecular do not exist. All your knowledge is limited. You could not find out that kind of molecular. So how you can still make this stable microemulsion? The general way is that I can choose a two surfactant with known HLB value. I choose one surfactant has the HLB value lower than the HLB value of the liquid mixture. Choose another surfactant with the HLB value higher than the liquid. Then I play with the ratio. Play with the ratio of these two surfactants. You always be some value in between these two values. You always can fit the right ratio in order to match the HLB value of the liquid. This kind of strategy will be discussed again in the tutorial. Okay, so that way you can make a stable microemulsion. So okay, that's all for this microemulsion part. Next week we'll start to talk about the job. If you have any question, can come to discuss with me. Okay.